Okay, so the next one is exercise 31. It is simply 31, but because one of you asked for the chapter number, so I have decided to use this somewhat new scheme for numbering the exercises, where we first have the chapter number followed by the exercise number. So this one, for example, is the fifth chapter. It is the 31st exercise from the fifth chapter. So in this one, we have a permutation beta in the symmetric group of degree 7, S7, such that the fourth power of beta is this 7 cycle. We have to first of all find beta, that is the first part, and then in the second part, we have to find the possibilities for beta if under this same condition, beta is now coming from S9, the symmetric group of degree 9. So as you probably know, all the odd numbered exercises in this text either have their solutions or hints to their solutions at the back of the text. So this one also has a hint in which in fact the author has written the answer itself. So let us first see what Gallian, Let us first see what Gallian has written. In S7 we have beta equal to this 7 cycle 2, 4, 5, 7, 1, 3, 6. Now looking at this, you may feel happy that okay, so this is beta, and in fact if you calculate the fourth power of beta, you will see that you are getting this 7 cycle. But is that all? Of course not. For example, a question arises here: how do you know that this is the only beta for which the fourth power is this? You have to argue for that, because who knows, maybe there are other permutations also. So to arrive at this answer, we have to look at some things. We have to argue logically, and then only we can say, okay, this is the only possibility for beta. So the first observation here is this: because we are working in S7, so all the permutations we are dealing with are permutations on this set of 7 symbols. So let us consider that set. Now if one takes an element in this set, then one has this implication. And it's pretty easy and straightforward to see why this implication is true. If the hypothesis is true, and what is the hypothesis? The hypothesis is that beta does not change S, or in other words, beta fixes the element S. Then the fourth power of beta also does not change S, that is the conclusion. And it's pretty easy to see why that is so. If applying beta on S does not change S, then applying beta 4 times on S also will not change S. So this implication is true. So its contrapositive will also be true, which is the negation of the conclusion implying the negation of the hypothesis. This is the contrapositive of this, the implication above it. So this is just another way of saying the same thing. Okay. Now looking at beta to the power 4, which we in fact have, we know exactly what beta to the power 4 is, we see that this hypothesis of this implication, this one, not the one above, the hypothesis is true for all s belonging to S, because you see that beta to the power 4 does not fix anything. It changes all the symbols. It changes 1 to 4, 2 to 1, 3 to 5, 4 to 3, 5 to 6, and 6 to 7, and also 7 to 2. So that means, according to our analysis, according to our discussion, beta, whatever ultimately it turns out to be, also should change everything. Simply that is the consequence. So beta, we can write our conclusion like this: beta does not fix any element in S. Fine. Now, what is the consequence in turn of this fact on the cycle structure of beta? We already know that beta, being a permutation, can be represented as a product of disjoint cycles. So this one has a consequence on that structure, and the consequence is that in the representation of beta as a product of disjoint cycles, one cycles do not appear. When do we have one cycle? Say if your beta is this, beta is still coming from S7, okay? So if your beta is, for example, this, if this is beta, then clearly this is a representation of beta as a product of disjoint cycles. But we have one cycles here, which we normally do not write. Two one cycles we have. One of them is 6 and the other is 7. What this entire symbol says is that the image of 1 under beta is 2. The image of 2 under beta is 1. The image of 3 is 4, that of 4 is 5, that of 5 is 3. And the image of 6 is 6 itself, and the image of 7 is 7 itself. So those are fixed elements under beta, and that we don't have according to our discussion. So one cycles will not appear. And now that is why the possibility of expressing beta as a product of disjoint cycles has been restricted somewhat, to the extent that one cycles do not appear, or in other words, saying the same thing slightly differently, when you write beta as a product of disjoint cycles, all the symbols actually appear. Here, for example, you can see that 6 and 7 are not appearing. That will not be the case. Okay, now with this new information, what can we do? Let us now see. So we will now look at the possibilities for our beta as a product of disjoint cycles. There are of course still many possibilities, even with the restriction that one cycles do not appear, but we are definitely not going to look at actual numbers, actual cycles, but rather what can I say, the cycle structure of beta. For example, is beta a product of a 2 cycle and a 5 cycle, or is it a product of two cycles and a 3 cycle? So there are many possibilities. The only thing we have to keep in mind that in such a representation, all the 7 integers, all the 7 symbols must appear. So beta, for example, can have a cycle decomposition of this type. It's a product of a 2 cycle and a 5 cycle. Or it's a product of a 2 cycle and another 2 cycle and a 3 cycle. And keep in mind that these cycles are all disjoint. Symbols appearing in one cycle do not appear in the other cycles. That's what disjointness means. And I'm not sure if these are the only possibilities, except of course there is another one where beta is a 7 cycle, where in that single cycle all the symbols appear. Now I haven't really thought about any possible intermediate possibility here. Maybe there is something, but I don't want to think of it. The reason is that I want you to do that for me. Now our next aim is to show, or rather your next aim is to show that this is the only possible cycle structure for beta. The others are not possible. So how can we rule out the other possibilities? For the sake of argument, let us take this one first. Say beta is of this form. It's a product of a 2 cycle and a 5 cycle. Then what will beta to the power 4 be? Note that because the cycles are disjoint, they commute. Disjointness allows us to also write the same thing as this 5 cycle times this 2 cycle. The order does not matter. If the cycles are not disjoint, then of course the order will most likely in all the cases matter. But because of disjointness, you can in fact change the order at your will. And because of that commuting property, the 4th power of beta in fact is the product of the 4th powers of these cycles. You can make sense of this not by thinking of 4 or such a large thing. You just simply in a group, say you have 2 elements A and B in a group which commute. Okay, then you calculate the square of the product AB. By definition it is AB, AB. But because A and B commute, so in place of this middle BA, you can write AB. So you have A square, B square. So you can clearly, very naturally extend this. So the 4th power will also be the product of the 4th powers. Okay, now comes the, if you are thinking how can one possibly go beyond this, given that we really don't know what these stars are. It just simply everything now depends on the lengths of these cycles. We know that every 2 cycle has order 2. So if you find the square of a 2 cycle, you get identity. So that means the fourth power of a 2 cycle will also give you the identity permutation. And of course you have this. Now here I don't know what is going to happen, but at least I know this thing, and this is going to vanish because it's the identity permutation. Okay, now can this fourth power be equal to this? No, it can never be. Let's see why not. Note that we already have lost two symbols. Whatever these two stars are no longer present here. Now, no matter what you do with this 5 cycle, for example, in this case you will find its fourth power, you will take 4 copies of this 5 cycle and then multiply, and then something will happen. So whatever is going to happen will happen with these 5 symbols, and that calculation does not have the power to bring back those vanished 2 symbols, and that is why those 2 symbols will remain absent from the final answer, and that is why it can never be this 7 cycle. Whatever it ultimately turns out to be, it will never be this 7 cycle, simply due to the fact that we don't have 2 symbols, and here we have all the symbols. So this is not possible. Beta cannot be a product of a 2 cycle and a disjoint 5 cycle. In a similar manner, you will now in a very easy manner able to rule out the other possibilities, the others except this one, of course. So that will tell you that beta in fact has to be a 7 cycle. Okay, so after arguing this much, you now know that whatever beta is, it has to be a 7 cycle, and now we have to understand why beta is only this 7 cycle. Okay, so let us now go to that. So here we have seen what we had to see pretty much, so I am cleaning this part. Now, having seen this much, you may now think that you will just simply, by some argument, be able to immediately write beta because it's a 7 cycle, but still we need to put some effort. Beta is a 7 cycle. So let me write the form first. 1, 2, 3, 4, 5, 6, 7. Okay. So beta will definitely take 1 to something, and we now know that something is not 1, it is something else, some symbol other than 1. So we don't really know. I need somewhat more space to properly show you the calculation. So let me write like this. So we have 1 here. You know how a cycle is written, so that is why this next one is beta of 1. Then the next one is beta of this, that means beta square of 1. And this one is beta cube of 1, and this one is beta to the power 4 of 1. Now, although we may not be able to immediately say what beta of 1 is, but we know this one because we have beta to the power 4, and the image of 1 under beta to the power 4 is 4. So this thing is 4. Okay, so jumping some places, we have come to know that this is going to be 4. Okay, now we continue our calculation like this. This will be beta of 4, this will be beta square of 4, this will be beta cube of 4, which we now know anyway because we know we don't bother about it, and this will be beta to the power 4 of 4, which is 3. Then beta of 3, beta square of 3, beta cube of 3, beta to the power 4 of 3, which is 5. Beta of 5, beta square of 5, beta cube of 5, the fourth power of beta evaluated at 5 is 6. Then apply beta once, twice, 3 times, 4 times. That means this is the image of 6 under beta to the power 4. This is 7. And finally, beta 7, beta square 7, beta cube 7, beta to the power 4, 7 is 2. Let us now see whether we have got the same beta. 1 goes to 3, 3 goes to 6, 3 goes to 6, 6 goes to 2, 6 goes to 2, then 4, 5, 4, 5, 7, and 7 here comes back to 1, 7 goes to 1, because in writing a cycle only the cyclic order matters, so it does not matter where you start. In fact, you can see that these two things are the same function. That's what matters after all. So that's how you get beta. Now what I want you to do is that I actually want you to write the solution with all those arguments, because that way only you are able to first of all find this beta without just simply blindly looking for an answer to simply match this equation. And you also know one more thing, that this is the only beta, there can be no other beta. First we argued and we got the conclusion that beta has to be a 7 cycle, and then we now have seen that beta has to be precisely this 7 cycle. Okay, now we go to the second part. Now in this second part, our beta still satisfies this equation, but now it is coming from S9. So whatever is happening with these first 7 symbols from our new S has, besides these 7 symbols starting from 1 through 7, 8 and 9. Okay, so those new things are there. So you see, beta to the power 4 has to be this. So beta must behave exactly like this in the first part of our new set S, which has only the first 7 symbols. There is no other choice. But what beta is going to do with those additional symbols 8 and 9, there you will have exactly 2 possibilities, because beta is a permutation. So either beta will, that means our new beta considered as an element of S9. So beta will either fix 8, if it fixes 8 it has to fix 9, and also if it fixes 9 it has to fix 8, or it maps 8 to 9 and 9 to 8. So in S9 we have beta equal to the same thing or beta equal to this. Now the fact that in this new setting, in S line also we are simply saying that beta has to behave exactly like this with the first 7 symbols. That is not something very difficult to understand. If you have not understood it readily, I want you to again think of it. It's pretty easy to see that even if our new beta is larger, it acts on 2 extra symbols. But because it has to have its 4th power equal to this, so the part of beta acting on the first 7 symbols must be exactly this. Okay, you try to convince yourself why that is the case. And with the other 2 remaining symbols, of course, we see that there are exactly 2 possibilities. Had beta not been a permutation, there would have been other possibilities also. For example, you could have then thought of a function beta which first of all behaves like this, fine, but then it maps both 8 and 9 to 8. That will give you a function, but which of course is not a bijection because it's not one-to-one. But because of the bijective nature of beta, we have only these 2 possibilities. Okay, so that's just it. And here also you write, instead of just simply writing this like this, you at least write what I have said just now, that because beta has to behave like this, so it behaves like this, like before, with the first 7 symbols, and depending on how it behaves with the remaining 2, we have 2 possibilities. Okay, so that is your 31st one. Next, let beta be equal to this product of 3 cycles, 1, 4, 5. Right. Beta to the power 99 in disjoint cycle form. Oh, I have already written in disjoint cycle form. In spite of this high value of exponent, you can pretty much understand that because we have 3 cycles, when you calculate this exponent, the multiples of 3 will make things vanish, because 3 cycles have order 3. But you have to keep one thing in mind, that these cycles are not disjoint. Oh, did I say while I was writing this that beta is the product of these 2 disjoint 3 cycles? But if I said that, then that is wrong. Beta is the product of 2 3 cycles, but they are not disjoint. You have 1 here in both the cycles. So let us first write beta as a product of disjoint cycles. We do that first. We have beta equal to, keeping in mind that here the product is to be calculated by starting from what we have in the the rightmost one, and then we come towards the left side. So 1 goes to 4, and then 4 is unchanged by this. So 1 goes to 4. 1 is mapped into 4 by beta. Then 4 goes to 5, 5 is unchanged by this. So beta also maps 4 into 5. Then 5 goes to 1, and now that 1 is changed to 2. So 5 goes to 2. 2 is kept fixed by this one, and this one sends 2 to 3. 3 is kept fixed by this one, and this one sends 3 to 1. So 3 comes back to 1. And we have in fact all the symbols that have appeared here, 1, 2, 3, 4 and 5. So beta in fact, although it looks like this, it's in fact a 5 cycle, just that. Oh, so that means what I was saying initially now becomes useless, because we don't have to look at multiples of 3 but rather multiples of 5, because beta is a 5 cycle. Anyway, so let's see what happens now. So beta to the power 99 is equal to beta to the power 5 times 19 plus 4. Is this calculation all right? Let me just think of it. Yes, it's okay. So using the rules of exponent, you can write, because beta is after all coming from some symmetric group, right? It's coming from a group, so the rules of exponent are applicable. So using them, you can write like this. Now because our beta is a 5 cycle, so the 5th power of beta will be identity, the identity permutation. So that means we have beta to the power 4. So now you just have to calculate what beta to the power 4 is. So we have to apply beta to every symbol appearing here 4 times. So you apply that to 1 once, you get 4. 2 times you get 5. 3 times you get 2. 4 times you get 3. Okay, now comes 3. You apply beta to 3 once, you get 1. 2 you get 4. 3 times you get 5. 4 times you get 2. Then 2 goes to 3, that is 1, 1 that is 2, 4 that is 3, 5 that is 4. And finally 4 goes to 5, that is 1, and then 2 that is 2, 3 that is 3, and 1 that is 4. Wait, I think I messed up somewhere, no? Okay, why am I looking at 5? I next have to look at 4. Once, twice, 3 times, 4 times. So 4 is coming back to 1, and I think I have made a terrible mistake. I think I have made a mistake here. 2 goes to 3, that is once, then 1, that is 2 times we have applied beta. 3 times we apply beta, we get 4. 4 times we apply beta, we get, okay. So this is 5. This is not 4. Then 5 goes to 2, 3, 1, 4. And 4 goes to 5, 2, 3, 1. So 4 goes back to 1. So this is your 99th power of beta. Is that it? Yes. And because this itself is a cycle, so this is the expression of beta to the power 99 as a product of disjoint cycles. There is only one cycle. Next, find 3 elements. Sigma in S9 with the property that sigma cube is this permutation. One 157,283 times 469. Now here we have not been asked to find all sigmas satisfying this equation. Just 3 different sigmas are enough. The cubes of the following 3 permutations in S9 equal this thing. So let me write the permutations, and then of course the question like the first exercise today will arise. So we will look at that. Let us just first see what one can write. 8, 6, 7, 3, 9. This is one thing. Then 1, 4, 2, 5, 6, 8, 7, 9, 3. and one more, 2148 56379. Now this one is also an odd numbered exercise, so these are actually in fact available at the end of the book. So now again here, although we don't have to find all the sigmas satisfying this equation, but still at least let us see how one can in fact produce three different values of sigma which will all satisfy this. Note that there are three sets of symbols, disjoint symbols. One of the sets has these symbols 1, 5 and 7. The other one has 2, 8 and 3, and this one has 4, 6 and 9. Now look at the positions where these things are appearing in each of these 9 cycles. Each one of them is a 9 cycle. So let's circle these ones belonging to the first 3 cycles. 1, 5, 7, and let us put a bar over these ones 2, 8 and 3. So that leaves the other symbols, of course, which we can now instead of doing anything to them, we can just simply keep them as themselves. You can distinguish here also 1, 5, 7, then 2, 8, 3. Here also 1, 5, 7, 2, 8, 3. Okay. To compare these things, in fact, let us just slightly change this third cycle, third sigma, just like the ones before it, above it. We start here with 1, then we have 4, then 8, 5, 6, 3, 7, 9 and then 2. Now look at the way the different symbols have appeared in these 9 cycles. You see that the positions of 1, 5 and 7 have not changed actually, and the other things are changing. Okay, now the question arises, you can clearly see that there are 2 symbols from the other sets of symbols other than this first set, of course, in between this 1, 5 and 7. Here we have 2 symbols 2 and 4, here we have 2 symbols 8 and 6. Why is that so? That is because the cube of this sigma has to be equal to this. So that means the cube should map 1 to 5. So when you apply the cube to 1, you first of all apply this permutation to 1 once, you get 2. On that again you apply the same permutation, you get 4, and once more you get 5. So the cube of this maps 1 to 5. In a similar manner, 5 is mapped to 7 and 7 is again mapped back to 1. So that means the cube of this 9 cycle actually has this 3 cycle. Okay, but simply because of the appearance of some other things in between these 3 numbers, and those other things are not these 3 numbers. Okay, so that is why, simply because of that structure, the cube will give us this, and the same thing is true with the other sets of numbers also. you can see that between the any two adjacent or consecutive barred numbers 2, 8 and 3, again 2 something else is appearing from the other sets. So cube of this will also take 2 to 8, 8 to 3 and 3 back to 2. So we have 2, 8, 3, and because of a similar reason we have 4, 6, 9, because here also there is a gap of 2 places in between 2 consecutive symbols from the same set. Now to produce, okay, so you can now clearly see why the cube of this is this. Now what do you need to do to produce another such 9 cycle? You just change the positions of these sets, keeping in mind that between 2 consecutive elements from the same set you should have 2 objects from the other set, and this should be true for all the sets. So keeping that in mind, we are able to produce 2 other sigmas like this. What has the author done? He has first of all written 1, 5 and 7, and then he has decided to write 2, 8 and 3, okay, and then 4, 6 and 9. In this one, instead of writing 2 and 4, he has decided to write 4 and then 2. What is the difference? You see that the structure of these sets appearing here is the same as that appearing here. The structure is same, and because of that structure, the cube of this new sigma will also be equal to this. But now, because of this difference, these 2 permutations are different permutations. This one maps 1 to 2, this one maps 1 to 4. And although here it looks like just this one, I mean this bottom one looks in this region just like this one above it, but it is different elsewhere. This one maps 4 to 8, while this one maps 4 to 2. So these are 3 distinct sigmas whose cubes all equal this. Okay, so that's how one can guess these things. Next, what cycle is this thing? The inverse of this n cycle. The answer is pretty easy, and this one is immediate. Okay, do you see what this inverse is actually? I mean, I'm not asking you to immediately tell me. Of course, you cannot tell me over the internet, but I'm not asking you to think of the answer immediately, but try to think of what this in fact is. What is the meaning of this? The n cycle is a permutation, so that means it's a function. So it has an inverse because it's a bijective function, it's a permutation. What will that inverse be? That inverse will do the exact opposite thing to what the original function is doing. For example, the original cycle maps A1 to A2. So the inverse will map A2 to A1. This one maps A2 to A3. So the inverse will map A3 to A2. So the entire order will be reversed. And that is why the image of AN will now it will go in this direction, AN minus 1. The image of AN minus 1 will be AN minus 2. Instead of now going like this, we are going like this in the clockwise direction. And at one stage you will reach A2, whose image under the inverse map is A1, and the image of A1 under the inverse map is AN. Note that these two things in general are entirely different mappings. The original cycle and this cycle, this is also an N cycle. And if you are finding it still somewhat, okay, I need not write this final one. No. I can end the cycle notation here. If you are still somewhat confused about this inverse being this, you multiply this N cycle and the original N cycle, you will see that you are getting the identity permutation. So that will tell you that this has to be the inverse. So the question asks, what cycle is this? So this is the cycle. It is this cycle. It is also an N cycle. And let us solve one more. Let G be a group of permutations on a set X. Okay. Let A be an element in X, and we are going to define a subset of G based on A. So X is some set and G is a group of permutations on X. Note that since X is a set, you can consider the group of all permutations on X, which is your permutation group on X. I don't know if this notation is being used in this text. I don't remember. But the set of all permutations on X, which I am denoting like this, is also a group under composition of mappings. Now what this one says is that G is a group of permutations, not necessarily this one. What that simply means is that G is a subgroup of this and A is an element in our X. So normally we write capital S in place of X. This time around we are writing X. And keep in mind that this X, unlike the things we have seen so far, may be infinite also. And define stab of A, stab of A, to be the set of all permutations in G which fix this element A, because A is coming from X on which any element of G is a function. So you can evaluate that function at A. If that thing is equal to A, then that permutation belongs to stab A. That this stab A is called the stabilizer of A. It stabilizes or fixes A. It consists of all permutations which fix A. We call stab A the stabilizer. Yes. The stabilizer of the element A in G. Since it consists of those elements in G which fix A. Now what do we have to do? Prove that this stab A is a subgroup of G. Okay, so to prove that something is a subgroup of a group G, that thing should be a non-empty subset first of all. Note that the identity E in G belongs to the stabilizer of A. Why? Because the identity in G is nothing but the identity mapping on the set X, and the identity mapping fixes everything in X. In particular, it also fixes A. So E will belong to the stabilizer of A. So the stabilizer of A is a non-empty subset of G. It is a subset of G, no doubt. The definition itself says that, but it's now non-empty. Okay, now let alpha and beta be two elements in the stabilizer of A. Then alpha fixes A and beta also fixes A. So alpha beta also fixes A. Naturally, because both of them fix A, so their composition will also fix A. And alpha inverse also fixes A, because if the image of A under alpha is A, then the image of A under alpha inverse will also be A by the definition of the inverse of a bijective function. Hence, alpha beta and alpha inverse both belong to the stabilizer of A because they fix A. Thus, this is a subgroup of G, and that's what we wanted to show. So with this I am ending this video. Next we have our ring exercises video, also from Gallian. So see you in that video.